Hello everyone, thanks for coming. Today we are going to do a review of our week 2 lecture of linear algebra. In this week, introduce matrix multiplication, its relationship with Gaussian elimination, and then matrix inverses. There are three equivalent views of matrix multiplication. If we look at the different entries of the product of two matrices AB, then the elements are the ith column and ith row and jth column is the inner product of row I of A and column j of B. If we use the column-wise viewpoint, then each column of A equals to A times the columns of B. Similarly, each row of AB equals the row of A times B. So that is a linear combination of different rows of B and the linear combination of different columns of A. So those are two more linear algebra viewpoints for matrix multiplication. There are three key properties of matrix and matrix multiplications. One is the associative rule. AB times C equals to A times BC. Distributive rule. If A is multiplicable with B and can be multiplied with B and A can be multiplied with C, then A times B plus C equals to AB plus AC, while B plus C times D equals to BD plus CD. Generally, we don't have AB equals to BA. From one aspect, the shapes of the two matrices AB and BA they can be different. From the other aspect, even if both A and BA they are square matrices, there are lots of examples where AB does not equal to BA. Matrix multiplication actually represents the composition of linear transformations because each matrix would apply a linear transformation. So when we go back to Gaussian elimination, row operations transform AB into an equivalent system UX equals to C, where U is an upper triangular matrix, and this system is solved by back substitution. So what are we doing when we are doing the Gaussian elimination? Actually, we are multiplying elementary matrices to A to convert it into an upper triangular matrix. For example, if A is a 3 by 3 matrix, then we are finding three elementary matrices GFE such that U equals to GFEA. Then if we apply the inverses of those elementary matrices, then A equals to E inverse F inverse G inverse U, which is LU. So L equals to E inverse F inverse G inverse, and L is a lower triangular matrix. Also, its diagonal elements equal to 1. The diagonal entries of U are the pivots. So in this case, L and U they are not symmetric, because the diagonals of L are 1, but the diagonal elements of U may not be 1. So in this case, sometimes we also use the LDU factorization, A equals to LDU, where A, L, and U have unit diagonals, and D is the diagonal matrix of pivots. So the LU and LDU factorizations with unit diagonals are uniquely determined by A if A is non-singular. And if we learn matrix inverses, we'll show an elegant way of proving this property. Different elimination algorithms would change computation order, but actually the final factors of the LU factorization are unique. Later, we introduce the row exchange matrices called the permutation matrices. So row exchanges are required in the Gaussian elimination because sometimes the pivots may be 0 and we may need to exchange the sequence of rows. If A is non-singular, then there exists a suitable permutation P such that PA can be LU factorized. And in this case, AX equals to B has a unique solution. However, when A is singular, then no permutation would yield all pivots and Gaussian elimination will fail. In practice, larger pivots are chosen to reduce round-off error. That is to say, even if A is non-singular, sometimes we may also exchange the sequence of rows to create more numerically stable results. A good elimination code will store all the information P, the permutation matrix, L, the lower triangular matrix, and U, the upper triangular matrix. Essentially, we can break solving AX equals to B down into two fast triangular solvers, Ly equals to PB and Ux equals to Y, in order to get the solution X. Finally, we introduce the matrix inverse. The inverse, A inverse of a square matrix A satisfies A times A inverse equals to identity matrix, and A inverse times A equals to identity matrix. Note that only square matrix has an inverse. How do we find the inverse? So sometimes we can use the Gauss-Jordan method to get the new augmented matrix A and I, and then reduce it to AI, reduce the left side to I, and then the right hand side. The right side is inverse. Especially for 2x2 matrices, we have a quite convenient formula for A inverse. When does A inverse exist? A is only invertible if and only if it has n non-zero pivots when we are doing the Gaussian elimination plus some up to some permutation. So here are some important properties. The inverse of A times B equals to B inverse times A inverse in reverse order. The inverse of A inverse is A itself. The inverse of A transpose is A inverse transpose. Usually, it takes up to n cubic multiplications to get the inverse of an n by n matrix. Thanks for listening.